You can go, Mike.
Ready to go. Very good. Good morning. My name is Mike Heitzman, and I will be your host today for Kontur's webinar, which is going to talk about pavement density using dielectric mapping. Today's presentation will be an overview of the density profiling system developed through a transportation pooled fund program. It will include the importance of continuous density coverage to assess the quality of the asphalt pavement. The presentation will include examples using DPS technology on Minnesota paving projects. And it will highlight a trial implementation of a Kontur 3D DPS technology on a project where the challenges that were unique to the capabilities of this new form of DPS technology were able to overcome. This includes timely density information provided to the project engineer and his staff that they could then share with the paving contractor so that informed decisions could be made to manage the quality of the placed asphalt pavement mat density. Today's presentation will be made primarily by Dr. Kyle Hogue, and he is a researcher with the Minnesota Department of Transportation, and he specializes in non-destructive testing. He is the project manager of the Transportation Pooled Fund titled Continuous Asphalt Mixture Compaction Assessment using Pavement Density Profiling Systems. Kyle received his PhD in civil engineering from the University of Minnesota in 2013 and has been working with the Minnesota DOT for almost 10 years. Greg Johnson, the assistant bituminous engineer from the Minnesota DOT, will also assist Kyle with this presentation. During today's presentation, if you do have a question, please put that in the question box, and we will try to address them as needed. We definitely want to leave enough time for Kyle and Greg to get their presentations completed, and then we will address the questions towards the end. With that, I'm going to pass over the webinar to Kyle and let him begin his presentation.
Thank you very much, Mike. And yeah, thank you to Kent for setting this up. I'm excited to share some of the recent developments that Kontur has made to be able to do DPS analysis on asphalt pavement projects. So just to start us off here a little bit with kind of the full picture, I did want to go over our transportation pooled fund. That is a good way for all the different states and agencies to work with industry and manufacturers to try to advance this method and get it to a point where we can start implementing this exciting new technology for our asphalt pavement density assessment. So before we get into the presentation, it's obviously a pleasure working with Kontur, and they're a great group of vendors to work with here too. We also have done some testing with Earth Science System DPS, and our primary, at least to date, form of testing with density profiling systems is with this GSSI system that you see on the left. But yeah, like I said, great group of vendors to work with using GPR technology for this application, and happy to share what we've learned so far. And then, of course, thank you to Greg Johnson, our assistant bituminous engineer. I actually pulled him in on this presentation yesterday, so he is the best for doing a better job of introducing the application that we're going to share here later today than I would have been able to do. So just to begin with, this National Pooled Fund, what we're all about is trying to pull all the different interested state agencies and federal highway together to try to advance this technology. And ultimately, our goal is to provide comprehensive assessment of asphalt pavement. And that's currently uh, not being done in the practices right now for state agencies. Um, Frankly, we're using limited coring, which is a destructive method to do our density assessment, and density assessment is one of the, if not the most important construction factor in asphalt pavement to help them last longer. So what we're working towards is using this new technology to give a more complete assessment that we can use to incent good paving practices in that way. And actually also I wanted to mention Dr. Shangtao Dai and from Minnesota Department of Transportation and Steve Cooper from Federal Highway. This is really their brainchild um, to get us to the point where we're at today. So what we're all about, we do like to get together periodically, and what you see there on the lower left is our training and peer exchange opportunities. That was an example where we showed off some of the technology and showed the different levels of experience of the agencies and other DPS members, what the latest and greatest was. We put out these periodic informational materials that we're calling the DPS Digest. And ultimately, what we're doing is taking these full coverage density maps or dielectric, initially dielectric maps, and trying to combine them with other intelligent construction technologies to kind of tell the full picture of what's happening on our paving projects. And it's interesting that what kind of looks sometimes to be rather uh, random locations where you might see like a low spot in blue in the upper right figure there, indicating low density. It turns out they're not actually random. They're a function of paving practice, and in this case, a colder mat at placement resulted in lower density near the joint there. And then we'll also see an example later with looking at the breakdown roller passes and what happens when you don't have proper practice with that. I did put a link in the chat for those of you who are more into the cell phone technology. There's also the QR code there. Um, Basically, it's just a way for you to get connected if you're interested in what I have to present here today. So you can wait to fill that out and see if what I'm going to share here is of interest or not for you. And if so, it'll be great to work with you moving forward. We do have one of our kind of year-end peer exchange and project update events on October 28th through 30th. We're actually doing this in conjunction with continuous bituminous pavement stripping assessment through NDE Technologies, which incidentally is also led by MnDOT and includes some of the other use of Kontur technology that I'll be presenting here today. Again, that'll be in that survey. If you want to get connected, we do send out periodic emails with information. So let's get into the bulk of this. So um, ultimately, what we're doing is we're taking what's called the dielectric constant and measuring that right behind the final roller and creating a map of the dielectric constant behind the final roller. And the reason that's of value to us as a state agency is that directly correlates to the amount of air that's in the mix, which is commonly referred to as compaction or density. So for this to work, we need to make sure that we're uh, doing a good job of accurately characterizing the dielectric constant of everything that's not air in the mix, because the various mixes within your state and then from state to state can obviously have different dielectric properties. With that being said, it is a really simple method because the dielectric constant of air is 1, and the dielectric constant of everything else is going to be somewhere between 4 and 8. So as you might imagine, the more air you have in the mix, the lower your dielectric constant is going to be because the dielectric constant of air is 1. We've recently published through the pooled fund an AASHTO standard for this method to actually take these production mix samples and measure the dielectric constant of those. And we did some statistical tests to show the precision of the dielectric constant translates to within and actually better a repeatability than our currently accepted coring bulk specific gravity measurements. So with that, we feel like we have a pretty effective and reliable way to non-destructively monitor the dielectric properties of various mixes within Minnesota. And then as you see from this chart that the University of New Hampshire put together as part of the pooled fund, we can characterize mixes from throughout the country. And that's important because within each mix, these changes in air void content can accurately be assessed, but you can't just switch from mix to mix. So this is a way for us to basically lock into our mix, and then we can be pretty certain that these changes in dielectric are going to directly correspond to our high and low density locations out in the field. And within this procedure, it's a pretty simple method, and what you see on the left there is a couple different vendor setups that you can take these production mix pucks and basically shoot them for a dielectric, and we have a flow chart in place. Everybody loves flow charts that a technician can follow, and if everything passes, you can say, yes, this is an accurate representation of the dielectric properties of this specific mix on this specific day. And we track these samples and we use them for volumetrics anyway in the state of Minnesota. So this is kind of a nice, easy way to track our dielectric properties. And I did just want to give an actual real life example of how this can work. So basically all we're tracking is difference in predicted dielectric versus actual dielectric when we're tracking these production mix pucks day to day. And you can see relatively good agreement, except for one specific point here that corresponded to a section of pavement that was going to be placed around station 200. So just to give the group a kind of an idea of what that means and what caused that kind of a shift in our dielectric properties, we track all this stuff as state DOTs because we need to know what kind of mix we're paying for and what kind of changes are being made. And you can see here, this highlighted one is the one that caused that change in dielectric, where there's a blend change in the type of rocks that were being put in the mix in this case. So with that, we can go to our project and be pretty sure that we can track the dielectric changes and thus apply the appropriate mixing model when we're converting from dielectric to density. So here's an example of Highway 22 on a Minnesota project, and this is kind of just to give you as possible end users of the technology an idea of how we get to the full coverage maps that we'll be looking at today. So what you see here is just statistics of, on this specific project, we tested approximately 63 paving miles, which corresponded to over 500 DPS sensor passes with this technology here. And with this data, you can get your average density and your standard deviation of your density, but that just is the tip of the iceberg in terms of what type of information you can get. So, in order for us to get from what we're measuring, which is dielectric, to what we care about, which is density, one way to do it is just to plot the distribution or project the distribution based on the core results, which you see here on the left. And then you can also do the same thing with the hundreds of thousands of dielectrics. And if you have the mean and standard deviation of both, and you have a relatively normal distribution, you can come up with a regression that can convert your dielectric to density. However, we don't want to have to take all these cores just to get our conversion from dielectric to density. And we want to take advantage of the fact that we know that within each specific mix, we can predict what an incremental change of volumetric of air should do to our change in dielectric. And that's just based on the volumetrics of the mix and the dielectric properties of the surrounding material. So what you see here is actually two different predictions. One is using the actual full coverage data and full cores, and then the other is just using um, the mean core and dielectric values and using that in the mix model to make this prediction. And you see a very good agreement. So because we want to look into being able to use the mix model moving forward, what we did is we ended up breaking it down day by day in these different filter groups just to see what kind of agreement we can get between the kind of full picture where we need a full allotment of cores versus using the mix model once we lock it in to the mean density each day. And you see, again, good agreement for the most part, but there are some of these days where you see a little bit of a different in predicted based on the mix model, which is the darker line, versus what would be predicted based on the um, the full statistics. And this is broken down day by day. So the one of the factors here is that we have a limited amount of cores to be able to make this prediction with the lighter color lines. Uh, so as you might expect, the limited amount of cores actually does not do a very good job of being able to predict variability. So this is just a breakdown of day by day on a County Road 19 project, mean dielectric versus mean population core densities for the normal allotment of cores. And you can see even for a really tight window here, really good agreement when you're just looking at the mean. But now when we try to look at standard deviation, the cores are not adequate to be able to give us um, an effective variability. And that makes sense just logically when you're using hundreds of thousands of data points with the DPS versus in some cases less than 10 cores to try to get your variability from day to day. And that's where I think this DPS can really come in handy. So one way to look at this in terms of both your mean density and your variability is just to set your acceptance limits. So in this case, we're saying, okay, each one of these blue lines corresponds to 150 feet of paving. So this is a lot of data throughout the entire project. And we just want to know what percentage of our placed mat is within our acceptable limits. And you can set that using this software called Veda, which combines all the different intelligent construction technology tools to create these outputs. And you see a snapshot right away towards the center of this specific project where you started to see these 150-foot sublots below our what we're calling our acceptable level of density on within these 150-foot sublots. So the idea here now is we're paying incentive and disincentive based on these limited cores, but this technology is able to provide full coverage, hundreds of thousands of equivalent cores with our assessment. So the idea is to try to take this technology and figure out a way to be able to pay the contractors um, more money when they do a good job, which sounds simplistic, and pay them less money when there's more inconsistency with their mix. And we just simply can't do that with the cores because we don't have enough cores to be able to feel confident that we can do our payout based on that limited number of cores. So we still do incentive disincentive, but it's not at the uh, corresponding to the amount of actual effect on the pavement design life that getting good consistent density corresponds to. So what you see here is just broken down day by day, what this would look like in terms of a percent conformance spec. And we took this for some projects where we had cores and core incentives, and we had our full coverage density profiling system data, and just took a look at, so with just the cores, our day-to-day payout and incentives was almost $5,000 on this specific project of Highway 15. But then you look at the analysis and you see, okay, we have our 746,000 data points, and we have our histogram, but then we also can break this down to average density per 150-foot sublot. We can look at our acceptance per 150-foot sublot. We can even take a look at and break it down based on our just looking at our joint data, which is oftentimes the location of our pavement that's going to fail first. And you see, even though that on this specific project they were generally doing a great job, if you break it down to the joints, there were a significant amount of sections where we weren't necessarily seeing adequate density. So the idea again is to take a look at these projects, and here again, very similar when you just look at the average density and standard deviation on this Highway 1 project up in northern Minnesota. And in this case, just based on the cores, we're paying a little bit over $3,000 a day as an incentive. And now if we take a look at the analysis with the DPS, let's move forward to this percent conformance, and you just see nothing but uniform good results for the entire 150-foot sublots. So as you can imagine, and this holds true even for the core, even for the joint results too. And if you just go by the standard deviation and average density, these two projects look extremely similar. And in fact, in the one, you could even we even paid out more based on cores than what we're seeing with this full coverage data. So the idea is to take these incentives and disincentives and tie them to our full coverage is kind of our goal moving forward. So just with this ghost implementation, just comparing our actual core-based incentive disincentive versus our percent conformance, which we would look into using something like that for acceptance. You can see the cores did an okay job of assessing, but there's still these spots where it's kind of random luck if you're looking at the cores on how much the contractor is going to get paid each day. And as an agency, we're trying to limit our risk, and as a as a contractor, they're trying to limit their risk too. So I think, if we can do a more comprehensive full coverage analysis when we do these payouts, I think as an agency, we can pay out significantly more on these projects like the one you saw there, where it was just nothing but consistent, good compaction. That's a project that's going to last for a long time and save the taxpayers in Minnesota a lot of money just through the performance that they got with consistent density. The other factor that we can use density profiling systems for is to help with the quality management and give kind of feedback throughout the paving project. So what you see here is what's called echelon paving, where you can't really even see the joint. So this is the type of project where we shouldn't expect to see a difference in our joint density as compared to our mat density. And they do this by having side by side pavers and doing what's called hot on hot compaction, where they're able to send their roller compactors at the joint while the mix is hot in both lanes. And generally speaking, what we would see when we went out there, even with the sensor on the joint, is really good agreement between the joint and the two sensors that were not on the joint for the specific project. But we did see these periodic dips in, at this point, it's just dielectric throughout that project. So even mapping it out on a couple miles of data, the statistics still showed if you break it down on one side of the joint, still on average lower density than everywhere else on the mat. And this, of course, on echelon paving is something we want to eliminate. So we started to investigate, and one thing we always look at is the temperature at placement, and did see some corresponding low temperature mix corresponding to low density results, including some at that problematic joint location. But by and large, not too much of agreement there. Um, when we broke it down, no pun intended, to just the breakdown rollers, that turned out to kind of be our smoking gun in terms of what process improvement was needed to improve the density at that centerline joint location. And so what you see here with this red line at the bottom of your screen is locations near the joint where we only had one breakdown roller pass. And this corresponded one-to-one throughout this project with our low problematic, low density spots. And this is kind of where the random core luck comes in, where in this specific day, the core was taken just prior to one of these spots um, where the lack of a breakdown roller pass occurred and got passing density. So we gave this information to the contractor, and it turns out that the distance between the pavers was such that uh, the paver on the one side was lagging too far behind to the point where the breakdown roller, and again, this sounds simple, was just swerving around the adjacent paver and doing this periodically to kind of catch up to their paving operation in the adjacent lane. And of course, you know, if you're a contractor or you're a roller operator, you're just out there trying to do your job, and you don't necessarily always know that these type of decisions and this type of paving practice was really having a negative effect on the pavement life for this project. So these are the type of information that you can get from this full coverage mapping. So that gets us to this new Kontur 3D DPS. So what you see on the left is the new Kontur um, uh, method, I should say. So this is actually um, um, just the same contour antenna that you guys have probably seen, most of you, but just with a evaluation method that can convert it to a dielectric map. And then what you see on the right is kind of our typical three sensor method. So this map on the left was created for two separate lanes that had already been paved. And then what you see kind of this blue line down the center, it corresponds to the lower density that's at the joint between this traditional paving section that we tested. And then this section here is three passes back and forth on each lane, again corresponding the blue here at the joint using kind of this more traditional GPR DPS approach. So with that, we did have a project this year that actually was kind of the impetus for us trying to trial the Kontur DPS, where it was night paving. There was some issues with this specific project that our assistant bituminous engineer is going to get into here. And from a safety point of view, we needed a way of collecting this in a way that allowed us to collect at highway speed and give us the full coverage maps that the Kontur system can provide. So with that, I am going to pass it to Greg Johnson, who's going to kind of explain kind of what's unique and what traditional techniques we've done to take a look at this project that occurred earlier this year. So take it away, Greg.
Thank you, Kyle. Thank you for the all the information on the DPS of kind of how we got to where we were at here in Minnesota. As you know, our traditional way of doing things is taking 4-inch, 100 millimeter cores out in the pavement, destructive, and determining our density that way. That's still our standard in the spec. But as Kyle says, we're researching and moving towards a more full coverage because, like Kyle said, it's statistically just kind of luck of the draw where that core is going to land in any particular lot. So we're going to go through a case study here where we use the Kontur system instead of the 3-sensor GSSI system that we've used all over the state on this project in Minnesota. So go on to the next slide, Kyle. So here we are. If you don't know where Minnesota is, Minnesota's mid-continent, northern, I should say, mid-continent in the U.S. of A. As you see on the left side, there's a little red spot. If you can see it, it's just north of the metro, what we would call the metro area, where most of the population is in Minnesota. So on the left there is just a little zoomed in view. So here was sort of the go on to the next slide. That's perfect, Kyle. That's Kyle's managing the slides for me, so it may be a little herky jerky, but that's okay. This is Anoka County. Actually, I grew up in northern part of this county, but it's a basically relatively flat area of the state. Very, I'll say, sandy soils, fine sand soils. The water table is about probably 6 to 8 feet, but beneath the surface for most of the entire county, and there's lots of swamps, and mosquitoes are probably what it's biggestly known for. So, and that was sort of the problem that we had with a previous project on this, where MnDOT kind of got I'll say a little bit of a black eye because we had settlement issues the last time we reconstructed this road, and so it's like, okay, we don't want to go through that again because we have I'll say marginal to poor soils out there. Any I'll tell you this: instead of growing corn and soybeans, it's done in other parts of the state. The agricultural in the area is large sod fields that were basically drained swamps back in the day, that they grow grass for all the metro people that put up houses. So that's what's probably primarily the agriculture in the area. So that was sort of the soils that we're dealing with. So they're very stable until you put vibratory rollers on them. Then they become unstable and we start drawing moisture up towards the surface. So go on to the next slide, Kyle. So here's a little more zoomed in. It's, as you can see, it's a north-south, basically arterial road for MnDOT. Just off to the south is Minneapolis, St. Paul, the urban center, and this is sort of the I'll say arterial or collector road. Lots of traffic, 4-lane divided, and so all the paving on this or I should say most of the paving on this project was done at night, just so we were off the road during the daytime hours, so people could get to and from work, or to and from the businesses in the area. So most of the shots you're going to see are paving at night. So go on the next slide. So this project involved in most of it's like I showed 2 typicals, but most of the project is the top one. We're milling off 2.5 inches of pavement, basically just to get our smoothness back on this road. We're not doing anything really for structurally, and putting down a 2-inch lift of a dense graded asphalt pavement, and then on top of that we're putting a 5/8 of an inch or 16 millimeter what we call ultra thin bonded wearing course. Basically, it's a high asphalt high quality aggregate surface on the top that's very durable. So that's sort of what our project is. I'll get into why we went to the contour system in just a couple slides here, but I'm giving you a little details of what the kind of the construction that we're doing out there is. So next slide, Kyle. As you saw in other projects, MnDOT kind of a standard practice includes three things on projects: intelligent compaction and paver mounted thermal profiling we've had for a number of years. So that way we can track, what the frequency of that vibratory roller is, if it's a vibratory roller, frequency, amplitude, temperature of the mat, and where this roller has been or hasn't been. So when Kyle showed you that, hey, we only had one roller pass, that's because we have intelligent compaction on that, and we're tracking where every one of these rollers is going. We also have thermal mounted profiling, which is basically a temperature scanner right behind the screed on the paver. So we have a incentive disincentive off on that. We want to look for, basically give a tool that the contractor can use and that we can track, that we're looking for uniform temperature of that mixture coming out. So really good paving practices to make sure we have a good flow of material. We're just getting into and this is one of the projects that we had what we could call e-ticketing or MDMS or material data management system. Basically, we're tracking where every truck is at, how long it's been, in transit from the plant to the paver, how long it sat there in the queue before it dumped its load, anything like that. So we have a handle on trucks. So that's being used both for data management in terms of materials. We're also using it for project compliant for kind of our labor compliance sort of thing. So that's a whole separate issue that we won't get into.
Yeah,
Next
and
slide,
I can,
Kyle.
if you're all right with it, Greg, I can
Sure,
just add,
absolutely.
from a DPS perspective, I'm excited about the um, material delivery management system from the perspective that example that you saw earlier, where we did in fact have a change in dielectric properties in the mix. We can actually track where that mix is being placed with this type of technology. So that's, helps in that way too.
Right. Because now we know which truck brought it out, if they made it, if we had all of a sudden they got into a high moisture area out of a stockpile in a plant or something like that, and the mix is cooler coming out, we will see it, and you're going to find it probably with the DPS with a change in dielectric and density also. So just some kind of high level things of this project. Total project cost is about 33 million. As you see there, you kind of see the quantities that we're dealing with on this project. So it's it's not our biggest project we've ever done, but it's definitely one of the bigger ones since it's a 19-mile long project that we're doing out there. So go to the next slide, Kyle. So here's sort of the things why we are using the DPS system is because we had kind of that black eye when we were out there last year and had settlement issues, is that we specified in our contract documentation that all rollers had to be in static mode. So no vibratory rollers like or of those double steel wheel rollers that we typically use. So they had to all just keep the vibe part off and just go in static. So we said how many rollers they have to use. So they use, as we said, 2 steel and 3 pneumatic on the project. Since we were, I'll say MnDOT's taking on more of the risk, we actually waived all disincentives. We included all the incentives that they were going to take for any density measurements that we were taking like we normally would, but we waived all the disincentives. So really, we took a bunch of the risk off of the contractor at that point. But one of the things it's because we kind of took more risk on ourselves is we wanted a way to measure, hey, are we getting the quality of the pavement out there that we had that we wanted, and knowing that, hey, we would love to have full coverage out there, and doing it with just a push cart in an area that has, I'll say, lots of live traffic, because we were only shutting down one lane at a time, and doing it at night, and the project people are like, whatever you do out there, we're only going in the direction of traffic. There's no way we are going to use a device that you're going to turn around, you're going to have lights on, you're going to go back against traffic into the eyes of everybody that's in a car coming towards you. I said, nope, everything's always going in one direction. So that was kind of the impetus to say, okay, with the 3D DPS system, with Kontur has, which is more full width, we can just take one pass or down the road and get the information that we need. So go on to the next slide, Kyle. So like I said, all the incentives, disincentives were waived. As you see, this snapshot in time, we're getting average density about 90, a little over 93%. The contractor is getting I'll say plenty of money and incentives on this project. So obviously they are trying, even though we waived the disincentives, they are still going for density out there. So that was sort of the impetus. Kyle's now going to go into, all the data that we collected and how it actually looked. But I just gave you a little bit of a background of, the specifics on this case study of what the project was.
Thank you very much, Greg. So as promised, Greg, I'm a researcher, and Greg is the one who kind of keeps everything in check with me. So I was really happy to have Greg make himself available for this, because he did a much better job than I could have with getting you the kind of practical information and really laying out the importance of our 3D DPS mapping from an agency perspective, where we're taking on all this risk by waiving the disincentive. From our point of view, with these limited cores, we don't know if there's going to be some sections out there that the lack of vibratory roller passes was going to cause extremely low density. We just didn't know that before the project. So, and on the other hand, I think what also is nice, what Greg laid out here, is you can kind of see what kind of dollars are on the line here for contractors, even with what I would call somewhat limited incentive, disincentive in terms of what it actually means to the how long the pavement's going to life, and how long of life the pavement is going to be, and the associated dollar amount that you saw with having to do new construction up in the millions, right? So with that, I always like to say, before we get into the pretty pictures, that you have to be able to have a system in place to track and manage your data. And that includes not only the position of the data and when the data was collected, but how that fits with the paving practice. So luckily for us, or fortunately, I should say, our advanced materials testing team has these forms that are already in place to track the various paving each day, each lift, each lane. All these different things are tracked. And then we just have to correspond what we're measuring with our 3D DPS data to those already formed filter groups. So that's what you see here. You don't need to understand the details of all of this, but other than to say that if you go out there and do DPS testing, please document where you tested, when you tested, and correspond it obviously to the paving practices that day. So this kind of shows the first day that we were out there when they were paving, beginning down by County Highway 10 and then going up to State Highway 10 a little bit past. And what we were able to do kind of with this data is, let's just look at the dielectric variability and start to annotate here for the end users what we're seeing. So we saw maybe a little bit more variability and some transverse streaking at the beginning of the project. We saw a couple relatively low density stretches and things of that nature. And I did want to just go into the software to kind of show how you can look into this kind of stuff when you have these maps in your software. So just zooming in as we go along, this was just, again, like Greg said, we were able to get a single pass this first day for the traffic control constraints. And you can kind of just see the map of the relative density here. And we converted this to actual density here because we did have the production mix pucks and we're able to do that conversion. But you can kind of see periodically these spots that get down around 90% GMM in terms of our actual density when we were out there paving. So with nothing else, at least you're able to kind of initially here start to map out, okay, what am I seeing here on my project, and where are these potential spots that maybe we need to look into? So we had one here, looks like at if you zoom out, you can see actually which crossroad it was on. Okay, just shy of Highway 10 there. And then,
The off ramp. Yep.
yep, moving in closer. Oh yeah, that was the on-ramp. Yep. And then, yeah, then here just shy of Highway 10, again, another spot that you see kind of lower density. And you can see these relatively lower spots even before you convert it to density like we have here. So, and that's kind of where the fun, at least what I think is the fun part begins is, okay, so now we have these maps that are showing us where the relatively high and low density locations are. And now we can go to some of these other intelligent construction technologies and take a look of, okay, what was actually going on there? So this is actually here. Let me put it in full screen mode here. That same low spot, just with that you can find even initially with your dielectric map, corresponded to a paver stop. So on this project, as Greg said, there's a lot of traffic and a lot going on. So periodically, they did have to pull the paver and to other locations or trucking issues, whatever it was, stop the paving operation. And what happens often in those cases is you get cold mix getting placed, and that can result in some of the low density here that you see, and another paver stop just north of the highway towards the end of the paving that day, resulting in lower density results. And kind of believe it or not, seeing that there was a construction reason for these relatively lower spots actually gave us a little bit more comfort, because in this case we wanted to just make sure that restricting the contractor from being able to do their final or to do their vibratory rollers wasn't going to start to give us low density passes. So these relatively low spots were actually independent of that restriction. And for the most part, we saw a very uniform and a good density. So this just shows, again, another one where we started to see this maybe a little bit of transverse streaking. Again, the segregation really corresponding to the paver stops. And that was kind of our feedback to the contractor that, hey, you're doing a great job, but let's just try to limit our paver stops. And then, of course, you go
Kyle,
ahead, Greg. Yep.
can I explain one thing? Those long paver stops that you showed earlier. One of the things
Yep.
I didn't explain. It's 4-lane divided highway, but it's got I'll say every mile there is a signalized intersection. So when they're paving the left lane, as you saw there was live traffic on that right lane. So in order to pave kind of the median area where that road is gonna, and this went on every single intersection up the road and every mile, is that they'd have to stop the paver from that left lane and pull it in and do one, if not two, left turn lanes that were there, and sort of that center median right under the under the light. So that's kind of why there you see those long paper stops.
Thank you, Greg. Yeah. So as Greg said, I mean, there's typically a method to the madness of the contractor, and I think our role here is to try to just explain, okay, here is the results. Here's what happens when these different uh, um, choices are made, and sometimes they're logistically required for the type of closure that was done on these projects. So, and then again, I just wanted to have a slide here where we did have cores to ground truth, and it's good to see that the kind of high spots again were showing up high with the cores, and then even these relatively low spots were a 94% GMM, and that kind of gives us comfort that even these relatively low spots, they're getting adequate density on this project. And we did continue to do these analyses day to day, and again, here's another 2-hour period where they had to switch to pave 2 left turn lanes. That resulted in relatively lower density, but just for the most part, it was extremely uniform and high magnitude density on this project, which was kind of shocking, honestly, to me, in a situation where we're restricting their ability to use vibration on the project. So, we did monitor this day to day for the project, and continued to see consistent density with the 3D DPS results. And as an agency, I think we can feel really good about the product that we're getting on this project, even without having the core disincentives, because we did, as Greg said, had to waive that because we were kind of tying the contractor's hands behind their back by not allowing them to do the vibratory rollers. So with that, I did just want to briefly take my last couple minutes here to promote. We are starting our phase 2 of the pooled fund, and this is kind of just a list of some of the things that we're going to tackle as a group. And one of those certainly is going to be evaluating these improved data collection. So like I said, these vendors are working extremely hard, not just Kontur, but some of these other GPR vendors as well. But this breakthrough that we have with this Kontur antenna is big. We have 1-inch maps of 1-inch spacing maps that we can collect at highway speed. And we've seen really good results, as you saw here from the use of that. There's also some other exciting directions that do have their challenges with them, but trying to get more real-time feedback with getting GPR right on the roller compactors that we're looking into. And this is just kind of showing what we see as one way of getting the most out of this technology, where you can have this DPS technology on a roller to kind of let the roller compactor know when they're kind of leveling off. They've had enough passes to get as much compaction as they can get with that roller compactor, and then we can come and get our full density maps like what you've seen here in this presentation. And ideally, we'd like to get it to a point where we can feel confident and pay out incentive, disincentive based on these maps. And that's going to require continued development of the analysis techniques and making sure that what our maps show correspond to the high and low density locations. And like I said, I think one thing with this Kontur maps is we have these 1-inch by 1-inch maps. Now we can start to have a little bit of fun with the data, and this is just showing even a simple moving mean average. So an averaging filter to be able to take kind of this really granular data and then smooth it out to the level of analysis that we're looking at as a DOT. So we have a couple miles of data here. We really want to break it down, 150-foot sections or things of that nature. And then you can even do a little bit what I would call a more enhanced type filtering, like this kind of standard MATLAB one they were calling R loss, and both get the smoothing aspect of it to see these kind of low and high density spots, but also get a little bit of a sharper image to really dig down into our high and low density locations. And the main focus is on this implementation track, because we do think we're to the point with DPS where now we need to start to put it out there as something where we're actually paying incentive disincentive based on certainly the variability measures that we can get with these full coverage maps, if not eventually using the absolute density as well. With that, I did want to thank you for giving Greg and I some time here to share some of the DPS work we've been doing at Minnesota Department of Transportation, and like to take any questions that you might have.
Hey, Kyle, we do have quite a few interesting questions in the Q&A. So if you want to take a look at that, maybe start answering a couple of those.
Sure. And then if I answer some of these after is there a way to answer some of these after if we don't get to all of them as well? Okay.
Yeah, what we can do is if you wanted to just write some of these out, I can forward them to everyone who registered.
Perfect. All right, so let's go through these live. So any studies regarding the added pavement life when using full coverage DPS versus random cores? Not specifically. So Ulrich is actually from Maine DOT, and an active member of our pooled fund. So thanks for the question, Ulrich. We don't have any direct study of that because, frankly, we haven't used DPS as a form of incentive disincentive. We have used it as kind of a quality management tool, but again, that would be within the last couple years, and we'd still need to track those projects down the line, which is a pretty difficult thing to do with the different maintenance and preservation techniques that we do on pavements. But what I can say is that there's many studies, and people love to quote the Washington DOT study, where basically once you get below 92% GMM, every 1% drop below that reduces your pavement life by 10%. And you saw the numbers that Greg put up there in terms of what we're paying when we do a reconstruction on a large project like that. If we can even extend that 1, 2, 3 years, if not more, by getting a more consistent mat, you can do the math yourself out there on the type of savings we could see. So that's kind of the economic and business case for implementing this type of technology. And you did see that it does affect our actual quality that we get when we're giving feedback to the contractors. Farshad said, is there any reason you considered only GMM for the asphalt density in your regression model? Does GMB play any role in the model? I asked because air voids are a result of both GMM and GMB. Yes, so GMM, what was showed, is actually what is called percent GMM. So that's basically our percent max density that uses, as you said, GMB to be able to do that calculation. So what was presented here is percent GMM, percent max density. Are you using PMTP on the 5/8 inch or on the 2-inch layer? Okay, so
I can answer that, Kyle.
Yeah, go ahead, Greg.
So the answer is no. We're only doing the temperature measurements of the mat behind the screed on the thicker, dense graded. That thin, ultra thin that we put on top cools, I'll say, too quickly for where the sensor is shooting right behind the screed that we've seen when we have cool, windy days that we don't get accurate measurements. So we don't take any measurements on that.
Great. And then I can add, I know you didn't ask about DPS, but we also took results from DPS on that thinner section and did notice an effect of the underlying layer. So generally speaking, if it's bituminous on bituminous and you don't have much of a change in mixed properties, if it's a typical mill and overlay of 1.5 inches or more, there's not an effect of an underlying layer, but you do have to look into that for the thinner lifts like Ulrich was asking about. An anonymous attendee asked, is it possible to show an examiner how you came up with the density maps? We are using a kind of test case version. Kontur kind enough to provide us, Jacopo was able to provide us with a way of taking the data and processing the dielectric maps in Examiner. And he had an export function, so we could export those dielectrics out, which I was able to read into MATLAB and import them back using the layer, I think it was called layer or layer boundary or something like that. But I would leave it to Mike, or if Jacopo's on, to comment on if you're going to want people to export it to MATLAB like what I did and import it back, or if that's eventually going to be a feature in Examiner. We can maybe decide if that's worth a tutorial or not at some point.
Yeah, I think maybe Jacopo
Whoops, I think Mike
can
froze there.
address
Oh.
that in the response here for the final video.
Yeah, I don't know if
Oops.
Jacopo is on, but I do know we're going to have a further discussion of that. And actually, Kyle, if you could give this is a perfect point, just a 2-minute overview of your workflow using the Kontur system and what that kind of looked like in terms of your collection through Examiner, through everything else.
Sure. Okay, so here's Examiner, and what you see here are these, let's see if I can get here. Yeah, these interface that we've created, and basically what you get when you start with the Examiner software is kind of what you guys are familiar with, where you have your traces here and you have your regions. So if you right click on here, and um, you can go in and actually make sure that your region is the one that you want to analyze. And then once you're in the region that you want to analyze, you can create an interface here. So in this case, I would just click Draw Interface, and it would create kind of a placeholder for me. And then I could right click on that. And when I did that, I could create a new, or I could, let's see, export the interface as a point cloud, or I can't remember if it was a point cloud or data, but basically use the existing functionality of Examiner to export these dielectric maps into MATLAB. And then once I had it in MATLAB, then I could do all the normal operations that we do to convert dielectric to density, and then import it back into Examiner once we created a text file. But I don't believe that's going to be, and then here's the import interface data. So this is kind of our naming convention that we went over before in Excel. And as long as I had the right settings there and I had the right file name when I went into that file, then I can import it back into Examiner. And then you also have the ability to go in here and actually create your color maps. So I just cared about percent GMM between 90% and 100% for my color map. So I could set that here by adding a new interface in Examiner. I think that's probably the most in depth we want to go, at least for now, because I'm not sure again what you guys are planning for the final.
And we do have you've had kind of the I guess the introductory prototyping system in place, and we're coming up with a much more comprehensive and more push button idea for the Outlook. But could you also just, as a review, say on your collection about how fast were you doing the collection in terms of speed and coverage?
Yeah. So, and one thing I want to make clear is that to get the density maps, that's when I was exporting and importing back into Examiner. The dielectric maps, which give you your relative high and low densities, is all done within Examiner with the version that I was using.
And that's push button, correct? You're not doing any processing other than Examiner.
Correct. Yep. Yep. So, and then in terms of data collection speed, I think we had settings such that there's 54 pairs with this type of analysis to get our 1 inch spacing. And we had Greg Larson was our um, technician from the pavement office to do the data collection, and he could go up to, I think, 56 miles an hour at 6 inch spacing in the longitudinal direction. And then, of course, if we increase the to a foot, then it's well over any speed limit that you'd want to travel. So in this case, probably collecting around 40, 50 miles an hour on the project. So
Perfect.
yeah. I'm willing to stay
We're
over
good
and
on
answer all these questions.
if you want to
Okay.
continue answering, sure.
Yep. Okay. So, uh, what is the depth of the analysis, full depth or lift by lift? It's lift by lift, and it's most sensitive to, at least with the GSSI system, uh, to the top. Basically, half inch is what's the primary effect on our dielectric for that surface reflection method. Has MnDOT used this technology on bridge decks? I don't, is Dave on? Are they allowed to kind of clarify what they're asking? Because I think, if you're asking about contour in general, that would be a different question than using density profiling on bridge decks. And I'm not quite sure what Dave is asking there.
I just unmuted you, Dave, so you can talk if you like. Oop, might have a technology problem there.
Okay, no problem. So we are using contour technology for applications outside of 3D DPS, like what I presented here. And I know there's some states that are using it on bridge decks for things such as like corrosion detection of the rebars and delamination, that sort of stuff. But I'm not personally involved in any of that. So, um, okay, I kind of lost my spot. I was going in order there. Okay. Oh, paving bridges, Dave said in the chat. Um, we, I
We
Not specifically that I can remember. I know Rich Giesel from Alaska has showed some data where they restricted vibratory rolling on bridges, as most states do, and he saw a large drop in the density of the paving on the bridge um, with a DPS machine, and that was kind of one of the reasons I was kind of surprised in a good way that we got good results when we restricted vibratory rollers. But as Greg said, we kind of, with the 3 pneumatic rollers, tried to account for the fact that we didn't have uh, um, any vibratory
Okay,
rollers.
I'll say that I'll say most of MnDOT's bridge, or most of the bridges in the state, I should say, have a concrete bridge deck on them, and
Hmm.
we don't pave anything asphalt related on them.
Hmm. Thank you. So Dave said bridges often have membranes, so we don't want to core, right? Yeah, and let's see. I think Washington DOT was also looking into that. What you run into in those cases, and thanks for clarifying, Dave, because that's a good point, that this is a location that if we can get useful data on density on bridge decks, that's very useful, because if you can limit cores on bridge decks, that's a structural, even more of a structural improvement. Um, and what you also would run into there, if it's asphalt paving on a bridge deck, is depending on the lift thickness, if it's concrete below, that typically has a higher dielectric. So you have a higher dielectric contrast. So that's just one thing um, to look into if you try to apply this technology on a bridge deck. If you have less than an inch and a half or 2 inches, I would say, on top of concrete, you're probably going to get an effective underlying layer. So I wouldn't necessarily trust the dielectric map in that case for density. Anonymous attendee, what's the calibration process for the sensors? There's a few things that are kind of done by each vendor specifically, just to make sure their antennas are properly calibrated. There's an air test, which basically subtracts all the noise in the system. There's a metal test, which basically gives us the amount of energy that's being sent into the pavement at that specific height. And then in terms of calibration of the antenna to make sure it's giving us an accurate dielectric, with the GSSI system, we have a calibration block. So like a approximately 4.8 dielectric block that we measure to make sure our dielectric is within range there. And then there's various ways to obviously calibrate versus the cores, that you can get information on that on our website. Go ahead, Kent. Or you?
Yeah, and I actually just wanted to throw in a quick addition because it was coming off of this. So this was basically being tested with Kyle's help and a couple of groups in Europe also. And so this is now commercially available as a Kontur product on our Mark 6 line of antennas. So if you wanted to get further information specifically regarding your applications, just talk to either Dave Barry in the US, Americas, or Martin Magnuson in Europe, and we can help you out. But it is commercially available as a project and a product inside of the Kontur suite now.
Thank you. Yep. And then, of course, the other so calibration could mean a lot of different things. So the other, I guess, in that genre, that thing that we do, as I mentioned in the presentation, is monitor for changes in dielectric constant of the mix by doing the measurement of those production mix samples. And that's done with that AASHTO, following that AASHTO standard that I presented earlier. So then we had the dielectric constants are at specific depth or interface. It's measuring the surface dielectric constant. Will the chat moves around on me every time somebody does something?
It's my fault.
Will there
Sorry.
be a follow-up on this specific road years from now to justify the incentives? There could be, as I kind of mentioned with the Ulrich's question about kind of tracking to see did it actually last longer than it otherwise would have, that you need to be able to track what type of preservation treatments were done, what sort of maintenance was done on the road, and you still need to be able to track kind of how you're measuring pavement performance, crack count, all these different things. I think, it's a challenging problem to take that on, no question about it. And on the other hand, I don't know how much people are actually questioning whether or not a more consistent density map whether or not that is actually going to result in a longer lasting pavement. I don't think there's too much doubt about that. But obviously everything else equal, if somebody wants to take that on, that would be a great study to do. But yeah, again, you'd be getting into the weeds a little bit in terms of how to track performance and how to track what's actually been done to the pavement after the initial construction too, of course. And then each pavement is not an apples to apples comparison as well. So is it possible to measure dielectric when it's raining? No. Or how would you proceed if you cool the asphalt after placement? with water to increase cooling rate. Okay, so water is the enemy of this method, and I'm glad Elmar brought that up. So one way to attack this problem is, they even use water or a degreasing, some form of liquid degreasing on the final roller compactor themselves, which is less of a problem, kind of as Elmar alluded to, when the mat's 150 degrees or more. You see enough um, evaporation on the map that you can get a good, accurate dielectric map that corresponds to high and low density spots. Because really, what affects our dielectric is standing water on the surface for the most part. That's when it's a hot mat. When the mat cools and you get a significant rain event, all bets are off. And that's why, at least with this method, it's really suggested to try to get those measurements as soon as possible after paving's completed, both so you can get the information to the contractor as soon as possible, but then also to limit the chances that you're going to have any sort of a rain event after the mat has cooled, because in that case, it's kind of a function of your mat itself. And honestly, um, the spots that are going to dry last are probably your lower density locations where there's more voids at the surface. So if you have water sitting in those voids, they would actually show up as higher uh, than the surrounding area, which is the exact opposite of what we're looking at here. So how is the impact of moisture? Okay, we kind of covered that. Have you received questions from contractors challenging the results? Any insight on those conversations and liability discussion be helpful? Yeah. Um, so in Minnesota, I think our strategy, and here's where I'm going to rely on Greg to virtually kick me if I start getting out of line. Um, we Our strategy is to implement some of these new technologies as a quality management tool, and that is to say, require it as something that needs to be collected, but wait until we're at a point where we can feel all the kind of bugs of the logistics of data collection and making sure that our maps are representative of high and low density spots are ironed out before we start to come with the stick or the carrot, you know, based on this technology. And the thought process being there, if you still have cores that they're getting paid for incentive, disincentive, a lot of contractors aren't going to want to take the random do you feel lucky approach. They're going to want to use the full coverage maps to help and correct some of these systematic and process related things that are causing them to have a dip in density where they might get a ding on the cores. So from that point of view, um, I would say contentious. It's not as contentious, but uh, we have to be willing to pay for the data and be convinced that paying for that data is actually helping us get better pavement, even without having an incentive yet associated with the technology. And I think after you get kind of these report cards out, which Rebecca Embacher has worked with Bituminous on in the past, that's our advanced materials testing or technology unit. They get out report cards that say, hey, here's what you've been getting paid based on our current specs. Here's how you would get paid with our proposed specifications. And then, um, you know, some contractors are going to be happy if they're doing a good job, and some aren't going to be as happy if they're not doing as good of a job. But uh, kind of the liability aspect of that is we have to feel confident. Let's say we go initially with a variability spec and just say, hey, we want to make sure we don't have more than 10% of our 150-foot sublots 2% lower in density than the average that you hit that day. So something that's just based on uniformity of the mat, um, we have to be able to stand up to a claim where if we're paying out the contractors who are hitting that uniformity spec more than the ones who are not hitting that uniformity spec, um, if they were to say, well, I want to go take a core at that spot where you're saying I'm not meeting it, that's where we got to kind of lay it out in the spec and feel confident in the technology to be able to go forward with that. So I don't know, Greg, is there anything you would say to that?
I think the only other thing I'd add, Kyle, is we've sort of moved this technology. We did the IC and the thermal first. We did the thermal first, and then the IC came shortly afterwards. But they were basically get tools in the hands of the contractor, because we knew if we were coming behind with this full width DPS system that we eventually will do analysis on, that we wanted something on the front end that the contractors could use to see how well am I doing. Is there anything I can do to change my process real time? So we wanted something in their hands to begin with before we came with the stick, if you want to call it that,
Mhm.
eventually, maybe in the future, where we're actually going to use the data off the DPS to do pavement or analysis full width on that. We wanted something on the front end for them to use for their operation. So it's been kind of a, we're trying to package it together,
Mhm.
but we're still we're not all the way to the finish line yet, as Kyle's mentioned.
Yep. And then the next one is, thanks, Greg. That was helpful. Is the presentation available? I can send it to Kontur if you guys have a place to post it.
Yeah, we'll create a landing page with the presentation and the video recording.
And then we have a lot of presentations beyond just what MnDOT's been doing on that pooled fund website, that is linked in that Survey Monkey. Please elaborate on the through depth variation and which depth you use to evaluate the pavement. So it's going to be the surface, that's giving us our primary um, dielectric reading, and exactly what depth that corresponds to is probably a function of the wavelength of the system, and they're operating, well, Kontur is a step frequency, and GSSI is, I think, centered around 2 gigahertz. But kind of rule of thumb is basically it's characterizing, for the most part, that top half inch to inch of the pavement. I think I might have made it through them all. Is there any I'm missing that you can see, Kent?
There's some in the chat too, Kyle.
Oh, okay. All right. Okay. Okay. Thank you for the pre. What's the affecting factor to consider when putting the DPS on the roller? Um, I guess the way I would interpret that question is, um, what's the goal of putting it on um, the DPS on the roller, and then what might affect it if you do. So what people are having to deal with by putting DPS on the roller is vibration of the roller itself and moisture. And there's different ways that vendors, and I know um, Imad Al-Qadi at Illinois has tried to attack this problem. Um, and in terms of what's the goal of this, and what does it need to be able to do, I guess the good news for it being on the roller, in my opinion, for it to be useful, it basically just needs to tell, relatively speaking, when you're not really getting any more advantage with your rolling back and forth. So contractors might use like a spot check newt gauge to do that sort of stuff, um, and try to set their roller patterns and things of that nature. If you had a DPS sensor on the roller, it would just need to be accurate enough to kind of let the contractor know when they're starting to level off in terms of the advantage they're getting, um, each time they roll. Timo is here. All right. Is there a risk that if you start to do moving average and dielectric mapping, then you start to lose correlation with drill core results. Yeah, and that's his experience in Finland and Sweden. So one thing I would add to Timo's question and comment is that what's interesting about the dielectric mapping is that what we actually need to use those maps for in terms of assessment, like I said, a lot of times it's broken down into 150-foot sublots or more. And certainly even a 5-foot moving average would be more than enough in terms of being able to say, hey, this is a low spot or a high spot or deficient or not, and even breaking it down to statistics. But to compare it to cores, you need to have a much tighter window. But the only reason you need to compare it to cores isn't for anything to do with our ability to make the assessment. It's just to check how accurate our prediction of the density is. And it turns out that the amount of noise in your dielectric response as you average it out over, say, 6 inches, then 1 foot, then 5 foot, is a huge increase in precision and a huge drop in variability and noise as you average it out. So that's to say we can feel really confident in our assessment of the density, but then when we try to bring it back down to a 6-inch core, our variability is inherently higher. And you can model this too. Hang Lu from Hoda Azari's group in the Federal Highway has shown just the effect of surface characteristics when you're averaging it out over a 3-inch versus a 6-inch versus 1 foot and so on has a huge effect. So I think that's why maybe going more towards the population density from the cores and using a mixed model from there is a more appropriate way to do it, because inherently you're going to have a lot of noise in your dielectric if you're comparing it just to a 6-inch core. Does this technology work with soil such as sand? I have not applied it for that. I know people have used it to evaluate, I think, moisture variation for subgrades and things like that, but not density. The surface reflection kind of relies on a relatively flat surface. Otherwise, your changes in apparent dielectric are going to be actually affected by the roughness and unevenness of the surface if you apply it on a subgrade. And a compliment from Ulrich. So how about now? Did I reach all the questions, Kent? Or can you guys see any?
I think so. The only couple
ones?
that might be outstanding is it possible to measure dielectric when it's raining?
I did. Yeah, I did answer that one.
Right.
Yeah.
Okay. John Andrews, I think, has a question. Let's just see if he's available. John, you can talk if you come off mute.
Yes, I just want to comment. This is a very, very interesting and good presentation, and I'm looking for great things in the future. I think that the approach you're taking is accurate, methodical, and we're looking forward to being part of this process of delivering a more reliable product in the paving world. And I think that this is exciting work, and I want to thank you, Kyle, and your team of people for the quality of the work you've done.
Wow. Thanks, John. Appreciate it.
Excellent. Well, that's a good final comment to end on. Well, I appreciate everybody. And does anyone have anything last? Kyle, Greg, anything last?
Nope. Yeah, just thanks for joining us. And if you do want to continue to be part of the development of DPS, you saw the survey going out, and we'll use those results to make sure everyone's connected.
Excellent. And from the Kontur side, I want to say thank you very much to everybody. I think we lost Mike a couple of minutes ago. He was having a little bit of a problem with his internet connection. But from the Kontur standpoint, if you do have an interest in learning more about the Mark 6 system and we're trying this out, I'd love everybody's feedback with a new commercial name for the dielectric mapping, which is called DMAP. So give us an idea if you like thumbs up or thumbs down on that as a commercial name for it. So it's in the test mode right now. But you can talk to Dave Barry, dbarry@kontur.tech, or Martin Magnuson, mmagnuson@kontur.tech, to get further information, or you can email me. So thank you very much, everybody. Appreciate your time, and we will get the recording out probably Monday. And the presentation, we'll put it all up on a landing page and send that around to everybody.
All right. Thanks,
All
Kent.
right. Thanks,
Thanks,
guys.
everyone.
Have a great day.
Thank you.
All right. Bye.